Is there enough space for PV in Germany? Yes, there is enough space, and this can be achieved without major conflicts with agriculture or nature conservation. A key concept here is integration. Integrated photovoltaics make it possible to use land twice instead of once, which means additional land consumption for new PV plants can be greatly reduced or even avoided altogether. With integrated PV, solar systems are adapted to their surroundings and combined with other uses. For example, PV can be installed together with agriculture, on artificial lakes, as part of buildings, over car parks, along traffic routes, or even on vehicles. PV can also provide ecosystem services on renaturalized areas such as biotopes and peatlands. Relying on just one or two of these options isn't enough, given the urgency of the energy transition. We no longer have the time to test solutions one after another. Instead, all technically and socio-economically promising applications must be tested quickly and supported in an initial startup phase to unlock optimization and cost reduction potential through scaling and learning. Only after this broad startup phase can well-founded decisions be made about which applications and technologies to prioritize. Germany has just under 17 million hectares of agricultural land. Agrophotovoltaic allows this land to be used simultaneously for crop production and electricity generation. Agrophotovoltaic covers a wide range of applications, from intensive crops with specialized PV mounting systems to extensively used grassland with minimal PV adaptations and strong potential for ecosystem services. Overall, agrophotovoltaic increases land use efficiency and enables a massive expansion of PV capacity while preserving fertile soils for agriculture or combining farming with biodiversity enhancement. Although agrophotovoltaic is already deployed on a gigawatt scale worldwide, there are still only a few systems in Germany. With high-mounted agrophotovoltaic systems, crops can be grown in partial shade under the modules. Many crops show little or no yield loss under reduced irradiation, and some even benefit from it. If permanent crops such as orchards and vineyards are considered together with one-third of arable land excluding maize, this results in a technical potential of 1.7 terawatt peak, assuming an occupancy density of 0.6 megawatt peak per hectare. Systems with modules mounted closer to the ground and wide row spacing allow cultivation between the rows. Using vertical modules at an occupancy density of 0.25 megawatt peak per hectare, forage crop cultivation on permanent grassland alone adds a further 1.2 terawatt peak of technical potential. Around 13% of agricultural land in Germany is currently used for energy crops, mainly for biogas, biodiesel, vegetable oil, and bioethanol. This land use is significantly less efficient than agrophotovoltaic. Energy maize alone is grown on about 1 million hectares, which would correspond to roughly 600 gigawatt peak of PV capacity if converted to agrophotovoltaic with suitable crops, or to biodiversity-oriented PV systems. Opencast lignite mining has affected about 1,773 square kilometers in Germany, more than 3 times the area of Lake Constance. Many of these areas have already been flooded or are still being flooded, creating numerous artificial lakes. Altogether, this opens up a technical potential of around 45 gigawatt peak for floating PV. In active quarry lakes, floating PV can also support the self-supply of nearby production facilities and make use of existing grid connections. Worldwide, several gigawatts of floating PV are already installed. Germany has around 40 million buildings. Roofs and facades together offer a technical PV potential of roughly 1,000 gigawatt peak, considering only areas with sufficient solar irradiation and minimum connected size. At present, less than 10% of rooftop potential and less than 1 per mil of facade potential is being used. So far, PV deployment in Germany has focused mainly on rooftop systems, even though many building-integrated PV products are already certified and commercially available. These include PV roof tiles, lightweight PV systems for roofs with limited load-bearing capacity, PV for green roofs, facade-integrated modules, insulation systems with PV, opaque and semi-transparent PV glass, and PV shading elements. Building-integrated PV enables material-efficient solutions for steep roofs and allows the use of surfaces that would otherwise be unsuitable for aesthetic reasons. Conventional rooftop systems, however, have the advantage of being less dependent on construction and renovation cycles. According to the Federal Environment Agency, Germany has about 670 square kilometers of sealed settlement areas, excluding roads and railways. Parts of this area can be covered with PV modules for shading or with walkable PV systems, often referred to as urban PV. Germany's more than 300,000 large car parks alone represent a technical potential of about 59 gigawatt peak if covered with PV modules. Further gigawatt-scale potential comes from integrating PV into transport infrastructure, including noise barriers, PV canopies, horizontal surfaces, and rail tracks. PV canopies are particularly well suited for tunnel entrances and heavily trafficked urban roads. With the transition to electric mobility, vehicle surfaces themselves become relevant through vehicle-integrated PV, which can help increase driving range. How much of this technical potential can actually be realized depends on economic, regulatory, technical, and social factors, including public acceptance. In general, integrated PV systems tend to have somewhat higher electricity generation costs than simple open-space power plants. At the same time, they avoid land-use conflicts and create synergies, such as replacing building components, using existing infrastructure, or increasing the efficiency of electric vehicles.